Okay. Can everyone see my slides? Yeah.
Yes.
Okay, great. Yeah, so some brief outline. We'll go through in today's lectures the some definitions of this subject, this subdiscipline, and then we'll take a comparative perspective of the so-called idealized atmospheric boundary layer flows versus the canonical engineering flows that some of you with a mechanical engineering background have already seen it in your classes. And then we'll review some basic turbulence and statistics, which the Professor Gabby Catou from Duke graciously shared some of his slides, which I adapted from. And then for the next lecture, we'll especially focus on rough wall bounded flows, again, some comparative perspective compared to ABL flows over roughness, which is like one of the most simplified way for those of you or those of us who study the urban atmospheric boundary layer and the canopy flows, canopy meaning urban canopy or forest canopy or mixture of both. And then we'll, last but not least, go over some methods or overview some methods in ABL or boundary layer and micrometeorology. And so that will lead to subsequent discussions in the lectures in Dr. Zhu and Dr. Wang's two subsequent lectures focusing on like delving into each of the topics covered in these methods in a deeper in a deeper fashion. Okay, so those are my outlines. So Xiaowei, would you like to share yours? And so, the students could get an overview of what's coming up next, and then we can just go on with today's lecture, go to the details of today's lecture.
Yes, so would you mind to let us to share a screen?
Oh, yeah, of course, yeah, sorry, yeah, okay, so please go ahead.
Can you see my screen now?
Yeah.
So I will be talking about the CFD and turbulence modeling. As mentioned before, so I'm from the mechanical engineering department, and I get training all in the mechanical direction. So we are understanding the problem, or the environmental problem, from the perspective of the fluid. How does the fluid dynamics, how does the CFD works, and how could we combine this knowledge and also numerical approach to modeling the environmental problems. So I will have three parts. Part one will be talk about the computational fluid dynamics. So this part will be more generally talk about the fluid dynamics, general idea of the fluid dynamics, and also the general approach of numerical method. So part two, I will talk about the modeling of the turbulent flows. So this part, I will mention a little bit about the turbulent theory. How does turbulent theory can be applied in the environmental direction? So part three, I will talk about the numerical approach we are using, especially talking about the large eddy simulation, how to use the state-of-the-art simulation approach to simulate the problem we are interested in. So fundamentally, I will cover these three parts. Thank you.
Okay, great. Thanks, Xiaowei. Appreciate that. So now let's, without further ado, go to today's content. Let's see. Okay, so before we start, yeah, sorry, let me get rid of this. How can I minimize? Let me minimize this. Okay. Okay, so before we start, just some general comments. As Xiaowei and I both already repeatedly mentioned, this is a highly interdisciplinary field. And some goals of this crash course is for us from different kind of research backgrounds and experiences to learn the terminology or the kind of languages spoken by colleagues that's dealing with the same topic, but taking another or a slightly different approach or with a different research background. And the second goal is obviously we cannot cover everything in this just a 1 month course. And so the goal will be to, in those lectures, we want to give you guys some pointers to materials. And so you could have like a guidance to dive deeper for your research if you're interested in. And a little disclaimer here, what I'm talking about here is highly subjective to my own academic journey and experience, and of course, it's going to be biased. And it's not comprehensive at all. And so, and it's also the first time doing this crash course as part of the basically establishing this research network supported by the NSF, our NSF funded project for urban climate. And so, it's really our first time. And so afterward, if you have any suggestions and, comments, please let us know. Okay, so without further ado, let's go to the definitions. So micrometeorology is, you can consider this as a sub-branch.
I'm sorry, I don't think we can see the slide you're talking about if you are talking about a slide.
Yeah, oh, interesting. Can you
It looks like I can just see your desktop background.
Oh, okay. Yeah, thanks for mentioning. Yeah. Can you see this now?
I can see it now. Thank you.
Oh, okay, great. Yeah, thanks. Yeah, sorry about that. Okay, yeah, so that's before we start. And so atmospheric science, where micrometeorology is a sub-discipline of atmospheric science. And in terms of the atmospheric sciences, and in terms of different timescales of the problems or topics dealt with in atmospheric science. For example, in climate, excuse me, in climate, climate refers to this decadal mean circulations and trends in these variables in wind, temperature, and then on a shorter time scale, we have meteorology or weather. Oh, there is Chen Hao. Okay, so in the shorter time scale, especially these weekly variations in the state variables such as wind and the temperature fields, you can think of it or the weather as a chaotic realizations of the climate. And if we go to even shorter time scale, that is the boundary layer meteorology, that's usually occurring at a diurnal or less than 1 day time scale and of spatial scales of a few kilometers variations in the dynamics of the lower atmosphere. And what I want to point out is of paramount importance that is the surface forcing variability. And so these surface boundary conditions in terms of the boundary conditions of the momentum and the various scalars of the Earth's surfaces play a very important role, basically dictating the dynamics of boundary layer meteorology. Yeah. And so I will not read these definitions, but I will point out that if you have taken a boundary layer meteorology course in your respective institutions, and this textbook style 1988 is like one of the classic textbooks on boundary layer meteorology. And so this figure is illustrating different layers. So the boundary layer is roughly the lowest 1 to 2 kilometers from surface of the Earth. And then that's part of the troposphere. So that's the lower troposphere. And so you can read about these definitions and all these scales. So I will not go into them here. And if we even zoom into the atmospheric boundary layer or ABL closer, very close to the surface, which we call usually referred to as the lowest 10% of the atmospheric boundary layer, that is called the surface layer. And the micrometeorology is where essentially where the the subject deals with the bottom of the atmospheric boundary layer. And so ABL, it deals with the bottom part of the troposphere. And then you zoom into further, micrometeorology deals with even the bottom part of the surface of the ABL, which is called the surface layer. And this surface layer plays a very important role because first, all these exchange processes of energy gases between the atmosphere and the surface, the land surface, ocean surface, earth surface, they remain important topics for a wide range of applications. And also, since another part of this crash course is urban climate, and so that's where the human activities are most active. And so micrometeorology, of course, who studies the surface layer, the lowest, 100 or below 500 meters is where all the human activities are going on. And that's why micrometeorology plays a very important role in urban climate. And in terms of the time scale, the micrometeorology deals with the fluctuations. However, we also have microclimatology, which describes the time averaged or the long-term processes. Yeah. And so let's go a little bit deeper into micrometeorology. So what is micrometeorology? Again, you see these different layers shown here. And this domain, the surface layer, which is a small fraction of the atmospheric by volume, but it's essential for life. And that's where this discipline's micrometeorology is primarily interested in. Okay, so now we'll go to a comparative kind of perspective of the canonical engineering flow of especially turbulent boundary layers, compare that or versus the atmospheric boundary layer. So I'm sure a lot of you here are familiar with this schematic. And so this schematic is showing the kind of the simplest kind of external flow that one could have. So you have a flat plate with a sharp edge. And so when you have an oncoming flow, and so this oncoming flow with some free stream velocity is going to counter this sharp edge, and then a boundary layer develops downstream. And so this boundary layer development is going to lead to a boundary layer depth delta in the vertical direction. And so usually in the mechanical engineering or fluid mechanics context, the vertical direction, people use the y-axis to describe the vertical direction, whereas in the meteorological field, people use z to indicate the vertical direction. Yeah, but this is just an external flow, a simple boundary layer, and depending on the Reynolds number, and you could the boundary layer could transition from a laminar to turbulent ones. And so we see that we see a lot of parallel or analogy in the environmental flow. So let's look at this aerial picture. And so that this is New York City, and you have Manhattan and the Central Park. And so if you have on a clear day, clear weather day, you have a steady wind coming from the Hudson River from west to east. And this is this almost looks like essentially a sharp trailing edge, a flat plate, but with some roughness. Okay, so we'll go into more details of how this roughness changes the boundary layer. Yeah, but for now, let's forget about this roughness and just imagine that you could simplify the Earth's surface or the land surface as a piece of flat plate. So there are a lot of similarities. And so in order to appreciate these similarities in terms of the boundary layer flows in the canonical engineering context versus the ABL context, let's look at some more kind of quantitative descriptions of different layers or different vertical structures of these boundary layers. And then our goal is then to be able to match different layers in the mechanical engineering context into respective ones in the ABL context so that we gain a deeper understanding. And so for this, I'm referring to chapter 7 of the lectures in turbulence for the 21st century by Professor Bill George. And so this is from one of the turbulence courses I've taken at Princeton. And so what I'm going to go over here is a kind of a set of important relations and the results regarding turbulent wall-bounded flow, which is like the most basic mental model we want to have when we are studying its ABL counterpart. And we will see a lot of similarities and analogous behaviors between the two. And so the first one you can see that is the U star square, which is equal to the wall shear stress divided by the density. And so we're quite familiar with U star, which is friction velocity. People in meteorology also talk about the friction velocity. And this wall shear stress, if you recognize, this is the viscosity multiplied by the velocity gradient right at the wall where y is 0. There comes a very important result, which is called the constant stress layer or wall layer. And so this layer refers to where if you look at the Navier-Stokes equation and basically by appropriate scaling, so you can see chapter 7.4 for details, such that you can show from the equation. So it's a fundamental, it's an exact relation that the shear stress, wall shear stress is equal to 2 parts. It's made up of 2 parts. One is the Reynolds stress, the other is the viscous stress. And obviously, this is a constant. So within this wall layer, this relation holds. And so that's a constant stress. And this is true when the so-called the friction Reynolds number. Okay, the friction Reynolds number is defined in this way with the length scale being the boundary layer depth. When this Reynolds number, friction Reynolds number goes to infinity. So you can derive this result exactly. And so I have a quote here from the lectures directly. So this is one of the most important ideas in the history of boundary layer theory. And so this is the constant stress layer. And so for those of you who study meteorology, and you very often hear the term constant stress layer, and very often in practice in in ABL studies, we say that, okay, this constant stress layer roughly coincides with the surface layer. And this is where the surface stress or fluxes vary by less than 10%. So that's sort of the definition in the ABL, but we want to remember or remind ourselves that there is a fundamental kind of reason why we call this constant stress layer. And it all boils down to, you can derive this from the Navier-Stokes equation and considering the limit of the Reynolds number goes to infinity. And of course, in ABL flow, this condition is is a very good approximation. Okay, yeah. And then another two as in like layers of the turbulent boundary layer I want to mention is the so-called inner versus the outer turbulent boundary layer. And so those terms or terminologies come into play again and again in many papers you read. And so it's good to that you kind of master these languages. So what is an inner turbulent boundary layer? So this inner boundary layer refers to where that constant stress equation, which is this equation, where this equation holds. So that's that layer, or if you consider that depth of the turbulent boundary layer or the wall layer. And so of course, in this inner layer, we want to define the respective characteristic length scale and the velocity scale. So those are called the inner length scale and the inner velocity scale. And so for the inner length scale, is also referred to as eta. So don't confuse that with the Kolmogorov scale eta. Yeah, so this eta is the, you can see that the viscosity comes into play. And so one of the distinctive characteristics for the inner length scale is that you cannot ignore the effect of viscosity, right? And then for the inner velocity scale, that's the friction velocity. And so both of these length scales or the length scales and velocity scales, both of them lead to the so-called y plus coordinate. And so this y plus is referring to a non-dimensional way of expressing the vertical direction or the vertical height, y normalized by eta. So that's a y plus coordinate. Usually in fluid mechanics, we like to plot things in dimensionless axes. And so in the vertical, the distance is plotted in y plus, and then the variable will be, let's say if it's a velocity, it will be normalized by the inner velocity scale friction velocity. And in contrast to that, there is a outer turbulent boundary layer. And so in contrast to the inner, it's where the viscous stress term does not appear in the outer equation. And so we could define an outer length scale delta, which is the boundary layer depth, and also an outer velocity scale that is usually the free stream velocity. And of course, you can normalize the vertical direction define this outer coordinate by normalize the distance, vertical distance by the boundary layer depth. And what I want to mention here is one way to look at this friction velocity Reynolds number, this friction velocity Reynolds number. So this is the friction velocity Reynolds number is defined as the boundary layer depth multiplied by friction velocity and divided by viscosity. And another way to look at this is that we're essentially scaling the boundary layer depth by the inner scale, the inner length scale, okay? And so that's also a delta plus. And so in a way that knowing the Reynolds number, the friction Reynolds number is telling us about what is the scale, so-called scale separation between our boundary layer depth and then the wall layer depth. And so the higher the Reynolds number, the larger the scale separation. And then we basically, this relation then holds more true. Okay, so that's my, that's our brief review of turbulent wall-bounded flows. And now let's look at their details, the details of these different layers put into the context of a canonical turbulent boundary layer. And so let's first look at within the inner layer or wall layer, there could be different sublayers. So if you look at within this box, there will be the so-called linear sublayer where the y plus coordinate is smaller than 3. And if you look at the constant stress equation, within this layer, it's the viscous stress that dominates. And above that, you have a buffer layer. So that's the buffer layer. This is where both the turbulence effect and the viscous effect are important. And so this is where this equation holds. And beyond that, you have the inertial sublayer. So usually we do not talk too much about the mesolayer, but for the inertial sublayer, this is where the viscous effect can be ignored. Okay, and so if the viscous effect can be ignored, then the wall shear stress, the shear stress is simply only due to the Reynolds number. And this layer is important because soon you will see that that corresponds to the surface layer where we, in micrometeorology or ABL meteorology, we essentially put our sensors within the surface layer, and the sensors, by measuring the Reynolds stress or turbulent fluxes, are going to tell us about the surface conditions. And because of this, the inertial sublayer, the range where it exists, okay, and you can derive that the necessary condition for the existence of an inertial sublayer is therefore delta plus much greater than 300. Okay, so what is delta plus? Recall, so delta plus is just your roughness, sorry, not roughness, your friction velocity Reynolds number. Okay, so question for you to think about is in a typical ABL flow, is this condition satisfied? That is, we need to have this sufficiently high scale separation between the boundary layer height and the inner layer depth or wall layer for a inertial sublayer to exist. So is this satisfied? Yeah, you can think about it. Yeah. So I will not go into detail about the outer boundary layer because mostly for the micrometeorology, we deal with the surface layer. And you can see that in terms of the upper bound of the inertial sublayer is 0.1 of the roughly 0.1 of the outer layer coordinate, the outer coordinate. And so that is why in boundary layer meteorology or micrometeorology, we always say that, oh, the surface layer is 10%, roughly 10% of the boundary layer height. Yeah. Okay, so now a comparison, which will kind of map the canonical turbulent bounded flow to our understanding of these ABL flows. So you can see that it is essentially the whole inner layer where the inner equation applies, or the wall layer that is mapped into the surface layer. Okay, so a summary here, the surface layer equivalent is equivalently the wall layer. It's just that the meteorologists call this surface layer, where people in mechanical engineering call this wall layer or inner layer. And it's the surface layer that micrometeorology mainly focuses on. And within the inner layer or the wall layer, we will have a viscous sublayer. So the viscous sublayer includes both the buffer and the linear, where the effect of viscosity or viscous stress is is important. And we usually do not distinguish the meson layer and the inertial sublayer. You just need to remember that is the Reynolds stress dominates there for the shear stress. And I also want to emphasize here is that we call this inertial sublayer, this entire thing, overlap region, because this is called overlap. And that is because both the inner and outer equations were scaling applied. So if you recall our definition of the outer scaling, or the outer turbulent boundary layer is that the viscous stress term does not appear. Okay, and so that's why in the essentially the overlap, the inertial sublayer, both the inner and outer equations were scaling up. Okay. Any questions before we move on? Looking at these structures. Okay, no questions. So
I have one question.
Yeah, sure.
So for the page 12.
Which one? Sorry.
Page 12, the previous page.
Previous page.
Yes. Yeah.
Yeah.
So here, you mean the necessary condition for existence of initial sublayer is dirt much bigger than 300.
Right.
So
Yeah.
how do we get this number out? Just like that.
Yeah. So if you just look at this equation, right? So the inertial sublayer exists between y plus from 30 to 0.1, delta plus. Okay.
Yeah.
And so this just means that you want the y plus to be basically greater than 300. Yeah.
Okay.
I also have two questions. The
Yeah,
first
sure.
one is slide number 11. The first equation you mentioned, equation for wall shear stress.
Yeah.
In that part, you use mu, but in the second equation below, when you calculate the constant stress layer, you replace mu with nu. I know the second one is viscosity. The first one is also viscosity, right?
Yeah. I think let's see. Yeah. So because this one you divide by the density, so this is the dynamic
Oh,
viscosity, right?
I see.
Yeah.
Yeah.
Yeah. So
Right.
I divided by
Oh,
rho.
right. Yes. Yes.
Yeah.
Okay. And another question is, perhaps you can also briefly explain why on slide 13 we have both y plus and y bar in the
Okay.
vertical direction.
Yeah, great question. Yeah, so when we have the y plus, this is where we focus on studying the wall region or the inner region, where everything is expressed in terms of the wall units. So-called wall units are using like variables scaled by the inner length scale and the inner velocity scale. But however, if we look at the outer layer, that is where the viscosity effect does not matter, we typically just scale the boundary layer height, scale the vertical direction with the boundary layer height. So essentially, if you look at the outer coordinate, this is 10% of the outer layer. So within the 10% of the outer layer, that is your wall layer, where the inner equation apply, but they do have an overlap region. And so that overlap region, it can be either expressed in terms of the outer scaling or the inner scaling. So that's where the inertial sublayer concepts then apply. Yeah.
Thank you.
Sure. So let's just move on. Yeah. Well, what else are different? So how are the idealized ABL flows versus canonical engineering flows? What else are different? Can someone or students volunteer and say, if you have experience working with a wind tunnel versus if you just go outside and look at a sunny day in Oklahoma, which probably is very hot. So what's the difference? Are you all too shy to say something? Okay, so let's move on then. Can you see my slides? Okay, great.
Yes.
Okay, so yeah. So in canonical turbulent boundary layer, like a typical wind tunnel, the density changes are negligible, where we typically ignore the density changes. However, in the atmosphere, the density changes are not negligible. And that is because the lower atmosphere is constantly subject to the solar radiation. And the thermodynamics of the lower atmosphere then plays a very important role. Okay, so if we take a step back and start from the mass conservation equation as what is shown here. So this is the general form of mass conservation equation. But the ABL flows, they can still be reduced to incompressible flows, where this mass conservation or this continuity equation can still take the form of an incompressible flow, as shown here, despite significant density variations. Okay, and so if you want to delve into the details, in textbook style, there is one chapter talks about different approximations, the shallow convection approximations and the shallow vertical motion, basically the shallow vertical motion approximations to exactly show why this continuity or the incompressible flow condition is still valid for ABL flow. Yeah, so but now I want to maybe let's shift the focus on just on the density stratification in the ABL, because I regard this as one of the most important differences between the canonical engineering turbulent boundary layer and the ABL. Yeah, so but if you guys have any other thoughts or questions or comments about this difference, you're welcome to chime in, or yeah. But for the students, I think if you will want to get a deeper appreciation of the density stratification, thermodynamics is very important. And so if we just consider the ideal gas law, so ideal gas law, you can regard this as one simplest form of the equation of thermodynamic states. And so when we talk about thermodynamic states of the air, essentially we're saying that the thermodynamic state of the pressure, temperature, and the volume obeys some function. And this, if it's a ideal gas law, then these state variables, they're constrained by the ideal gas law. And so this is PV equals nRT, where P is equal to rho R divided by M times T, where M is the molar mass. So that's just the ideal gas law. And for the air or gases in a considerable vertical span, that is the ABL over 1 kilometer, we know that the pressure varies with altitude. And so if you consider an air parcel, let's say in a hot summer day, the surface is heated and you have this hot air parcel that's rising to a few kilometers, not a few kilometers, sorry, a few hundred meters up in the atmosphere, in the ABL, and the pressure of this parcel actually adjusts very fast. And it's much faster than the temperature exchange between the parcel and its surrounding fluid. And so when this parcel moves to a new height, its temperature and the density, because its pressure changes, adjusts. But the ideal gas law in the parcel is still obeyed. And so its temperature and the density, which are the other two thermodynamic states, will then adjust according to the thermodynamic, the equation of thermodynamic states, or the ideal gas law. Yeah. And so this is called the density stratified flow, because we see that the density change to adjust according to the vertical pressure variation. Yeah, but luckily, the ABL, the vertical motions, are only 1 kilometer. And so that will allow us to simplify a lot of things, and like incompressibility, and later we talk about the Boussinesq approximations. So this eventually will only result in a, so this is the material derivative, meaning that we're following this parcel, this air parcel, following its trajectory, and calculating how its density changes. And so this d rho dt is still small enough such that the incompressibility condition, or the incompressible continuity equation, still remains applicable for such a shallow motion. So this is like the one of the criterion for the shallow motions, shallow convective motions. Okay, so there comes the Boussinesq approximation, which you will hear quite a bit if you deal with turbulent boundary layers in the atmospheric context. So if let's start with some two conditions. One is the hydrostatic condition, and the other is the ideal gas law. So the air obeys ideal gas law. We can derive that essentially the pressure varies with height according to this equation. Okay, and so this equation is essentially telling us that we could define a E folding pressure change height that is called the atmospheric scale height. And so this atmospheric scale height is around 8.5 kilometers. Okay, and so when the vertical motions in the ABL are much smaller than this scale height, which is satisfied for most of the ABL flows, that's where the shallow convection part plays in. So, it's shallow, it's only 1 kilometer. So it's not exceeding the scale height. And so this implies that the vertical variations are too small to cause a large change in the velocity field divergence. And so the incompressibility condition can still roughly apply. And when the flow velocity divergence does not cause a change in density, and so this means that the density in the ABL does not vary due to dynamics of the flow. So as in when, if you have the air or wind is moving the air around, and such motion is not going to cause a change in the density. So this is essentially what this second condition means. And when both condition, when you apply both conditions, then you arrive at the so-called Boussinesq approximation. And so a consequence of the Boussinesq approximation is that we can consider this density perturbation of rho, or the density, when it's only important when if you are considered a vertical momentum balance. That means the density variation is only important for the vertical movement of air, and also it's only important in the body force, okay, not in other terms. So this will become clearer in the next slide. Any questions before we go on? Yeah. And so I'm just putting out this equation here, so you recognize that this is the basically the Navier-Stokes equation, and we have the body force due to gravity here, and if we apply the Boussinesq approximation, which is the density perturbation is only important for vertical momentum balance, and it's only important when it's multiplied by G, which is the body force. And so we can show that, essentially we end up with this term. And this term has two parts. One is the usual gravitational force. So that's the body force. And the other is due to the density perturbation. So the density perturbation in the gravitational field, what is that? That is just a buoyancy force. Okay, and so essentially another thing we could derive by considering the ideal gas law, which I'm not going to derive here. Again, if you're interested, refer to the relevant chapters in Stahl, is that we can relate the density perturbation relative to its equilibrium state into the virtual potential temperature perturbation. And so if you make this adjustment, you can replace this term by the virtual potential temperature perturbation. And this is advantageous because temperature is easier to measure than density. Okay. Yeah. So those are the more technical parts of the density stratified flow. Or density stratification, which is one of the most important distinctions between the ABL and the canonical turbulent boundary layer. Yeah. And of course, we see that the effect of buoyancy in terms of generating turbulence, and that is quite one of the important mechanisms generating turbulence in the ABL. Yeah. And of course, the effect of buoyancy, how is that going to change the surface layer dynamics? That will come into play when, especially in next lecture, we're going to introduce this Monod-Albuquerque similarity theory, which is, you can think of it as a basically a buoyancy correction to the inner wall, or to the inner boundary layer. Okay. Can we move? Well, yeah. So you can see this is a some effect of the density stratification in a convective ABL. So I made these simulations using direct numerical simulations and a visualization called a vapor. And so you can see these like thermal plumes, and it's rising up to the top of the boundary layer and mixing the scalars across the boundary layer. Yeah, so these are the vertical motions, and they're like also moving towards the downstream direction. So it's basically like a mixed convective boundary layer we have. Yeah. Okay. Any other questions before we move on to the second part? So which is like a basic review of turbulence and statistics. Okay, we're good.
Maybe just like a clarification question.
Yeah,
on
sure.
slide 19, I think we often also use some like similar terminology to refer to different types of turbulence. We have mechanical turbulence and also thermally driven turbulence. Here, just want to make it clear, thermally driven turbulence is essentially similar to this buoyancy turbulence.
Yes.
And maybe I think you also mentioned one term called body force, right?
Yes, yeah.
Yeah.
Yes. So
shall we like briefly explain
oh
that?
yeah,
to our
sure,
students?
yeah. That would be great. Yeah. So let me let me explain a little bit. And so the two types of forces acting on fluids. One is the surface force, where you know the surface shear pressure is all considered as like acting on the surface of a control volume, whereas the body force is also called the volume force. And it's because of the a finite volume of a particle or a fluid parcel that or a fluid parcel has a finite volume. And that volume, if it's placed in some field, either gravitational field or an electromagnetic field, it is going to give you a force that's proportional to the volume of this parcel. Yeah, so it's just like a buoyancy, you know, think of the usual buoyant force. Yeah.
Thank you.
Sure, yeah. So this is maybe a more like a fluid mechanics, mechanical engineering kind of way explaining things. Yeah. Any other questions from our students?
Yes. Hi, Professor Lee. I have a quick question.
Sure.
So, how can we know whether the Bose-Nask assumption can be applied to urban surface layer?
Yeah.
What is the criteria?
Yeah. So that's a very good question for the urban surface layer. People usually when they say, okay, Bose-Nask approximation applies for the atmospheric boundary layer, you know, usually it requires that the speed of the flow is very small, and you know the density variation is small, in various criterion. In a more general, like ABL context. But I've not seen one, you know, specifically analyze whether this is good for in an urban context. And so maybe, you know, if you're interested, you could think about in an urban context, what could have changed those criterion, like for the Bose-Nask approximation. Yeah, do you get a speed of flow that's very high? I don't know, maybe because of the presence of these tall buildings. Well, I don't know. Yeah, but that's a good point. Yeah. Okay, so shall we let's move on then. I want to yeah, because we'll post the slides, we'll post the readings. And so I will go through the second part in the remaining 30 minutes, about 30 minutes, pretty fast, just to give you an overview of what is out there. Yeah, so for those of you who have taken the turbulence course, or those of you who have not taken the turbulence course, it really doesn't matter. We'll give you some brief review. And so there's really no universal definition of what turbulent flows are. But there are only some so-called defining syndromes of turbulence. And so first, turbulent flows are really three-dimensional. And because only with three-dimensionality, you can have you can generate a rotation. And so that distinguishes turbulence from the waves, okay? And turbulent flows are also dissipative. And so this being dissipative means that the turbulent flows are active over many scales and they are time irreversible. And so the mechanical energy contained in the turbulent flow is eventually going to be dissipated as heat, as the turbulent motions, you know, basically are doing work against each other because of the viscosity. So they're eventually turning into heat, which is irreversible. Yeah, so I will not go into the details here, but that's a very interesting perspective of time irreversibility or reversibility. And so if you're interested, look at these slides. And another thing I want to maybe emphasize here is that we often compare turbulence and the chaos or a chaotic system. But what are the differences or how similar they are? And so in this paper, they consider a simple kind of equation that describes a chaotic system called a logistic equation. So this is a logistic equation where the state at the next time step t+1 can be derived from the previous time step, so on and so forth. And you can show by manipulating this equation that this can be turned into the red term plus the green plus this one, the blue and this light blue one. And the advantage of writing this is that then you compare with your Navier-Stokes equation, and all of a sudden you see that, oh, this red term represents the so-called tendency term or this time derivative. And this term, which is a nonlinear term, this nonlinear term is our convective or advective term. And this is a linear term, and this is a viscosity term, and there's a constant and that corresponds to the pressure and the gravity force. Yeah, and so essentially the turbulence as if you think of it as a chaotic system, is that they could have a short-term predictability, but in the long term or long run, there's no predictability, and only a statistical predictability can be achieved. So what it means by that is if you consider this simple model for turbulence or chaotic system, this logistic equation, if you vary the initial condition by a decimal place of the fifth decimal place difference, then in the beginning, this red line and the black line, they still coincide, but as time goes, you see that these two solutions diverge. So that's why we call you cannot get a long-term predictability, long-term deterministic predictability. However, you can still get a statistical predictability of the blue, of the red and the black, if you consider the probability density function or the PDF of the solution. So you can see that they match with each other, and so that's a manifestation of using this simple logistic system to understand the nature of turbulence being chaotic. Yeah, so you can, and that's why when we study turbulence, essentially we apply the concept of ensemble average in the sense that we think of we could conduct the experiment as in multiple universe. Okay, and so in one universe you conduct the experiment, and another realization you conduct the same experiment in another universe, so on and so forth, until you gather all these different time series that describe the same system, but they are performed at ideally multiple universe. But of course, we do not have multiple universe coexisting in reality. And that's why we repeatedly perform the experiments to build up a ensemble of the data and then average across these ensembles statistically to understand turbulence. Yeah. And when it comes to environmental flows, what I want to emphasize here is that we often think of the environmental flows as being made up of the mean flows, the waves, and the turbulence. And so you can read up these definitions about what these three things are. Yeah, but essentially for turbulence, I want to emphasize here is that, if you're interested in studying turbulence in the urban canopy or urban boundary layer, this is like the wind gusts or gustiness imposed on the mean flow field. And turbulence, one thing is that it is very efficient in mixing the heat, humidity, and the energy and various tracers. Yeah, some visualizations I will skip here, and also a very fun paper talking about the artistics in interpretation of turbulence, namely Da Vinci's interpretation of turbulence and how he applied all these concepts in his drawings. Yeah, so I will not go into the details here. If you're interested, look at these papers. But there comes another important concept or terminology that's called eddies. So we often talk about eddies, but what they are. You know, if you look at the atmospheric boundary layer flows, you don't really see the eddies. So because they're just some conceptual ways for us to understand the multi-scale nature of turbulence. Yeah, so, but they can be conceived as a so-called parcel of fluid of some size moving coherently, creating some kind of these swirling motions. And the important thing is that you think of the turbulent flow eddies being having a wide range of scales. Yeah, and larger scales, they have small, larger scale eddies have smaller eddies embedded in them. And so it's like a, you know, it's like a fractal thing, if you want to think about it. And so if you want to delve deeper into turbulence, then you look at the turbulent motions in its, essentially look at those energy spectra of turbulent motions, and you will be able to distinguish different eddy sizes that correspond to different ranges of the so-called energy spectrum, the dissipation range, the inertial range, and the energy production range. And so this magenta color corresponds to the energy production range, where it corresponds to the eddies of the largest size. And so these eddies of the largest size in a typical ABL corresponds to or is commensurate with the boundary layer depths. So like about 1 kilometer, these large scale eddies. And so they're responsible for producing the turbulence, and they're subject to different boundary conditions. And then these larger scale eddies have smaller ones embedded in them. And these eddies, they can break down from large ones to small ones. So that's why they undergo the so-called cascade. So cascade meaning that the scales of the eddies change from large to smaller ones. And in this cascade range, we call them the inertial range. And so they correspond to these mid-size eddies. These mid-size eddies can further break down because of the actions of turbulent of fluid viscosity. So these small eddies, they like rotate against each other, and this viscosity is going to eventually break them down and generate heat. And so these are called a dissipation range. So these are the smallest ones. Yeah, but of course, this is just a very qualitative overview of the different eddy ranges. And so if you're interested, take a class on that. Yeah. And so now we have some basic knowledge of the defining syndromes of turbulence, but for you know, us who are interested in studying or concerned about how turbulence affect the mean transport of momentum and scalars, you know, we want to appreciate how turbulence is helping the mean transport of momentum and scalars. And so I want to introduce this field experiment. And so this field experiment has been conducted in Switzerland, in Lake Geneva, and where micrometeorologists set up their instruments and the high frequency sensors called the sonic anemometers, and you see these 3 claws. And so they're sending sound signals and using the principle of Doppler shift to deduce velocity at high or motion of air at high frequency, usually above 10 hertz or 20 hertz. And this is a way to understand how the turbulent fluctuation is playing a role in basically dictating the motions of air. And these are quite expensive measurements because, measuring a signal at a high frequency, essentially, that's very expensive. So various instruments set up in this platform, and micrometeorologists use these high frequency measurements of temperature and velocity and also humidity to study how turbulence is helping the transport. Yeah, so to give you a taste of how the data looks like, So you can see that what we are plotting here is the fluctuating component of, so I will explain what fluctuating means. So the fluctuating components of humidity and the vertical velocity. And so you can see that if the measurement is at 20 Hertz, and so for 30 seconds, we have 600 data points here. So that's the fluctuating component of humidity, and that's the vertical velocity. So to quantify the mean transport, let's say, of water vapor flux, that essentially boils down to how do we statistically quantify the effect of turbulence in transporting the water vapor. And that requires us to take the turbulent motion in a statistical sense. And so there comes two important concepts. One is called the Reynolds decomposition, and the other is the Reynolds averaging rules. And so by applying these statistical measures to the essentially those high frequency time series, we are able to quantify or calculate the effect of turbulence on the transport of water vapor. Okay, so I'm not going into these details, but what I want to emphasize here is that if you get a chance, you may want to review some of the basic statistics or probability, such as the definition of a PDF or and the CDF, and also the definition of statistical moments. Okay, so this is a definition of the nth statistical moment, or the nth moment about the origin, given a basically a probability density function of some random variable x. And so the first order moment is usually called the mean. And so you recognize that this is like a basically summation of every realization of the random variable x, and then divide this or average this for the sample size. And then the second order moment, or the square root of that, is called the standard deviation, so on and so forth. And the skewness coefficient is related to the third moment. And recall that these are, we see the summation signs, okay, instead of these integration signs. And so in a way that these are the empirical estimates of the statistical moments given our experimental data or experimental samples. And these experimental samples, how many of them we have? We have n number of samples. And so these relations to estimate the real so-called population moment is only true if you establish a large sample size. Yeah. Right, so another concept is the ensembles and realizations. And so these, I want to, we touched upon these, the ensembles, why we need ensemble averages or realizations. So you can review this on your own. But essentially, let's now go to the Reynolds decomposition. That will allow us to, for example, calculate or quantify this turbulent transport. Essentially, in the ABL, we can perform Reynolds decomposition because of the existence of the so-called spectral gap. So what is a spectral gap? A spectral gap refers to if we consider the atmospheric motion, the whole atmospheric motion, and then look at their variability in terms of the cycles or their temporal frequencies, or the hour of variability. And so we can see that we have the synoptic scales, which vary on the order of beyond about 100 hours or 10 hours. So that's the energy scale. And then between the synoptic scale and the turbulent scale, usually we'll find that there is not much going on in terms of the atmospheric motion. And so therefore, we have a gap in between these two scales, the large scale and the small scale. And therefore, the implication is that when we're analyzing or when we're doing micrometeorology research in the surface layer, who are concerned about the turbulent scales, we can assume that there is a given stationary synoptic scale or synoptic condition. And under that synoptic condition, we only care about how the small scales, they themselves are basically interacting with each other without worrying about the non-stationarity imposed by the so-called large scale boundary condition. And so, yeah, we can then, so this like momentarily freeze the whatever signals of these high frequency measurements we take in the surface layer, and simply just analyze those small scales. Yeah. And that's why we can decompose the signals or these measurements we perform in the surface layer using those high frequency instruments as the two parts. One is the mean. So the mean does not vary below, let's say, below 1 hour. So below 1 hour, the mean stays constant. And the fluctuating component or any deviation from the mean is only due to the small scale motion and has nothing to do with the variability in the large scale. And so in a way that by performing the decomposition with the spectral gap, we can, the fluctuating component is then only due to turbulent motion. But of course, this is an assumption. And in reality, those called sub-mesoscale motions are going to affect the turbulence. And that's like kind of a research. But essentially, the spectral gap allows us to decompose the signals into the mean and fluctuating part for various variables important in boundary layer meteorology. And then also the rules of averaging, again, if you have this textbook, if you have taken it, learned this in other courses, it's a good time to review this. Yeah. So these are the averaging rules. So with these averaging rules, I'll skip this, and you can basically calculate the turbulent transport of water vapor, let's say using those experimental data of that lake field experiment for the water vapor flux. Yeah, so I'm not going to go through the derivations here. Yeah. Okay, the last part is about now, if we take a step back and jump out of the empirical context. So now, before it's like we're applying this Reynolds decomposition to the experimental quantities we measure, but we can similarly apply this Reynolds averaging and Reynolds decomposition to all the conservation equations and see what we get. And so this is a way that allows us to maybe derive the so-called prognostic equations for the higher order statistical moments. And so you can refer to the style chapter 3 and 4 for all these derivations. And so what I want to emphasize here is that we need to pay special attention to the so-called convective or advective term in various conservation equations. And so they are the important terms that will eventually give rise to the higher order terms. So for example, in the Navier-Stokes equation, this is the convective term. And by doing the Reynolds decomposition and the Reynolds average, you end up with a higher order term. So this higher order term consists of the product of two fluctuating components of the velocity Reynolds averaged. Yeah. And then you can do this, not just for the one, excuse me, one equation, but you can further derive a prognostic equation for these higher order terms. And so if you do that, you realize that you have another even higher order term. That is the product of 3 fluctuating components. And then if you derive another prognostic equation for the products of these 3 fluctuating components, you'll end up with, even another equation. Yeah. And so on and so forth. And so this essentially is called a turbulence closure problem, where we always end up with an unknown higher order term. And that results in 1 fewer equation than the number of unknowns. So that's called the turbulence closure problem. And our way to tackle turbulence in boundary layer meteorology or micrometeorology, or in other applications in the urban context, a lot of that has to do with how to deal with coming up with another equation to represent this unknown, right? And so a question for you to think about is that what is special about this advective or convective term in the budget equation that will, after you can basically do the Reynolds average, you result in this higher order term. So what's special about it? Yeah. Any questions? Yeah. So I will end this presentation and the lecture here, because I think this is a good point to end, leaving you guys a question about the turbulence closure problem. And so in the next week, we're going to essentially finishing up the discussion of the turbulence closure. And so that will be, this part will be related to the kind of computational fluid dynamics modeling, turbulence modeling that Xiaowei is going to talk about, okay, in the in his lecture, in his upcoming lecture. And for next time, we're going to review some canopy flow concepts and rough wall boundary flows concept, and then go over some of the important detail in the methodologies here. Okay, so that will be it for today. So do we have questions? We have a few more minutes for discussions before we go. Yeah.
So for the reading material you mentioned, probably we will put it in the Dropbox, or
yeah, sure. We can put it in a Dropbox and share with the share with students and with students of our close collaborators. And yeah, so the link will contain all the slides we have. Yeah.
Nice. Yes. Thanks.
Thank you. I appreciate that. Coming from a mechanical engineering background, I don't necessarily know which are the good textbooks when it comes to civil and environmental engineering.
Yeah, a lot of the time is that you find people call different or similar things, different names, or different things with the same name, and that's so confusing. Yeah, so I hope this will be a good opportunity for us to clarify some of these confusion, or especially in terms of the terminologies, and so we're all on the same page in terms of we can speak a common language. Yeah. Okay, any other questions, comments? And so it will be my turn next week as well. So I will give another lecture, and then we'll hand this over to Xiaowei, and then will be Chenhao. Okay. Yeah. Thanks a lot.
So will you give some homework to students, some questions or something? No?
Well, I don't know. You guys already have a lot of stuff on your plate, and probably you're busy with research assigned by your advisor. So maybe we'll start with this. What's special about the convective or the advective term? Yeah.
Yes, that's good. Okay, thank you.
Thank you, everyone. So I'll see you same time next week. Yeah, bye.
Thank you, Chi. Bye.
Thank you so much. Bye.
Thank you.
Thank you. Bye.